Okay, welcome everyone to the ArtIAMAS seminar series, which is co-organized by University of Maryland, Baltimore County, University of Maryland, College Park, and Army Research Lab. We are fortunate to have Dr. Nikhil Chopra as a distinguished speaker for today. The title of his talk is Iterative Preconditioning for Accelerating Machine Learning Problems. Dr. Nikhil Chopra is a professor in the Department of Mechanical Engineering at the University of Maryland, College Park. He received a Bachelor of Technology degree in Mechanical Engineering from the Indian Institute of Technology, Kharagpur, in 2001. And right after that, he has received his master's degree in General Engineering in 2003 and a PhD degree in Systems and Entrepreneurial Engineering in 2006 from the University of Illinois, Urbana-Champaign. His current research interests are in the areas of nonlinear control, robotics, and machine learning. His current, he is the co-author of the book titled Passively Based Control and Estimation in Networked Robotics. He is currently an associate editor of Automatica Journal and was previously an associate editor of IEEE Transaction on Control of Network Systems and IEEE Transaction on Automatic Control. Without further ado, Dr. Chopra, take it ahead.
Thanks, Munalia. Thanks for the invitation for giving this talk. So today I'm going to be talking about iterative preconditioning for accelerating machine learning problems. So this is kind of the outline for the talk. It's kind of a summary of, in some ways, what research we have done on this topic. And, we'll start with essentially the, what we'd call learning for linear parameterization, in a sense like, your things that you are trying to figure out are linearly parameterized in your cost. And, how can you accelerate those kind of problems? And then, once the data is noisy, how does it impact the solution? And how does it compare with other methods which are out there to solve these kind of problems? And then you basically, we treat this kind of over general communication graph. So these are distributed problems that we are trying to address. I will show you what I mean by that exactly. And then we kind of head to more general, nonlinear convex cost functions. And then in the end, we'll kind of see how we are trying to apply it to a distributed beamforming, kind of the problem that we're working on in the ArtIAMAS project here. So my collaborators on this project, on this work essentially are Kushal Chakrabarti, right, Nirupam Gupta, and from ARL have Jeffrey Twigg, Ricardo Dagafu, and Amrit Vedi, who was earlier at ARL, and now he's at UMD. And so this work has been kind of partly funded by PSMA project, and the recent work on beamforming has been kind of is funded by the ArtIAMAS project here. So what kind of problems we are interested in? So first is the beamforming problem. So essentially here you have a bunch of robots, right? And they are trying to essentially use their kind of signal transmissions in a coherent way to kind of achieve, in some ways a very directional signal in some directions. But at the same time, they want that there should be this signals kind of has a null or is kind of, is not kind of, it can't be detected by some other directions, right? So how do you generate these kind of patterns? So you can pose this as a distributed optimization problem, and we'll just kind of see the application later today. Also, for example, you can have a bunch of, UAVs or any sensors. Let's, for example, they're tracking a person, right? So, so how do you do coordinated tracking of a person or an entity or an object of interest, right? That can also be formulated as a kind of a distributed optimization problem. We are trying to essentially reduce the uncertainty in their estimate and, figure that out. So other applications are more broader, which go into like kind of trying to optimize for energy utilization and stuff like that. So one of the things that that kind of motivates this distributed application is that the data may not reside that you're using to kind of estimate or learn may not reside at one place. It may be residing in multiple servers, or it may be either not located in one place, or if it's located in one place, maybe you're using different GPUs because the data is too large and you want to accelerate it. So how do you kind of treat this kind of problem, basically, where data is distributed, right? And either a central coordinator is trying to figure out, right, estimate or learn something from there, or you have kind of a more peer-to-peer network. So these are kind of the topology, kind of the communication topologies that we look at today specifically. So one is what we call a star topology. So in this case, they have a central coordinator, right? It's undirected communication. No data is shared, with the central coordinator. There's no data exchange happening. And gradients are kind of shared back and forth, and some of the information as well. But the data is kind of remains local. The same setting you can have peer-to-peer, where basically there is no central coordinator, but now you have a completely distributed or decentralized system, and you want to still figure out how to learn or do distributed optimization or decentralized optimization over this kind of a network. So these are the two kind of topologies that we'll kind of focus on today. So in the linear regression, this kind of turns out to be the problem that we look at specifically, right? So here I'll talk maybe a little bit more as I go about this in a few slides as well. But just to give you a heads up, essentially this is one of the problems that we'll work on today, and explore various things like if noise is there, how do you accelerate it and stuff like that. Right, and this is the more general problem where your cost is no longer linear. It's still convex, at least in the setting we're talking about today, but it's completely nonlinear. Okay, so these are kind of the two things that we'll talk about. So let's go first, dive into the first thing, where basically we are talking about where your parameters that you're trying to learn are linearly parameterized in your cost. So this is the setting we are interested in. So imagine you have a bunch of data, right? And the data is kind of sitting, and it could be data and its labels, for example, right? So A is a data, which is kind of you can think of it like your data points. If you have x1 till xn, right? They are kind of the rows of this A1 matrix, and B1 is as the corresponding labels, right? Similarly for other matrices as well. So now, if in this simple case, right, you may want to kind of learn what the kind of the parameter is that you're trying to learn, right? And the idea is that you want to jointly optimize this cost, right, across all agents, which is just kind of given by the linear regression cost that you see there on the slide, right? And the idea is you want to figure out the common x, right, which basically will kind of minimize this cost. So I'm putting some notations here on the right, and this will carry over for some slides. So just to kind of put the head into it. So basically, the thing we're trying to learn, the x vector, is d-dimensional, right? And these AIs are ni cross d kind of matrices, and B also has a corresponding ni. And so we'll see. So one point we want to make is that although this is a linear regression problem, a lot of machine learning problems, although they look highly nonlinear, can sometimes be formulated in this manner as well. So we'll see an example of that shortly as well. First, let's go to kind of a problem that is more kind of a distributed estimation problem that you see. For example, let's say I have a bunch of sensors, and this is like your pipeline, right? Essentially, I have some sensors on the pipeline. I have some pressure and flow sensors, and I'm trying to figure out by looking at at the sensor measurements at some places, can I figure out essentially some profile throughout the pipeline network? But this could be any sensor for that matter. And so, there's a problem in control systems known as kind of, designing an observer, a linear observer, right? And so you can think of, those who are familiar with control systems here, right? So you can always formulate kind of an observability problem as just by, knowing the initial state of the system. If you can figure out the initial state, I can figure out the state for all times because I know the A and B matrices. If those are not uncertain. So we can actually formulate that distributed state estimation problem or a distributed which is an observer problem in this manner as well. So we will show these results later, when we go later in the talk today. And now let's talk about a more kind of a classical machine learning problem, which is the classification problem. So think about, like, you have this data set, MNIST data set, which is very common. And, it basically is actually 16 pixel by 16 pixel images of 1 till, 9, right? And let's say you want to classify 1 versus digit 5 in that image. So if you take the image intensity, right, which is given, is basically a 256. The d vector that we talked about earlier will become 256. Okay, so it's and we kind of know that that the dimension is kind of in some ways directly kind of impacts my generalization capability in the machine learning problem, what I'm going to get out of it. So you could do a more complex kind of a neural network operation on this problem. But if you wanted to avoid that, you wanted to formulate this as a linear or a nonlinear regression problem, right? Which is still linear in the cost, but nonlinear in the features. We can design features cleverly. So for example, in this case, you see 2 features here. So instead of a 256 dimensional problem, this becomes a 2-dimensional, rather 3-dimensional, because there's always the bias term on top, which is the 1, right? So I can design this, what is called average intensity and average symmetry. And you can see that by doing these 2 features and then doing kind of a nonlinear feature transform, which is you see on the, which is, so this basically would have been A1 is, as you see, average intensity, A2 is symmetry, right? So, and then basically we can have some nonlinear feature transform, which is A1, A2, and A1 square, A2 square. And you can decide which is the best one by which is the best nonlinear transform by doing something like validation and whatnot, right? Cross validation, you can figure that out, which transform works best for your problem. But the point being that this problem I can formulate as a, this is a classification problem, but I can formulate this as a, a classification from kind of regression. So, we basically compute the regression problem and then we take the labels as -1 and +1, right? Instead of the real values that we typically do in regression, which is also real, but is very specific labels in this case. So you see that the curve that you get, is it's not overfitting at least, right? And has decent generalization in this case. And this is not highly optimized right now, but the point being that you can formulate these complex problems as linear, which are linear in the parameter. They may be nonlinear in the features, but they are still linear in the parameters. So what are the existing algorithms out there, right? So we have a variation of these. So I'm talking about, I'm leaving some algorithms out here, which we'll see later, which are kind of what to call adaptive gradient methods, like ADAM and so forth. We'll see them in the comparisons when we do numerical comparisons. But these are kind of the methods that are out there currently, right? And the method that we have, as you will see, we can actually get, in both linear and nonlinear cases, we can get superlinear convergence, which is faster than any of the existing methods. At least if you take adaptive gradient methods, right, you won't be able to achieve that kind of convergence rate. Some of the quasi-Newton methods achieve that, at least in a distributed case, you can achieve that, which are like BFGS, which is one of the popular ones, quasi-Newton methods. So what exactly is, what is conditioning? What is condition number? What is iterative conditioning? So think of this way, that I have a cost function, right? If I were to draw level sets of that cost function, which basically means I set the, whatever your cost is equal to some C, and I take various values of C here, right? You look at, let's say it's a 2-dimensional problem and you say see ellipses there, right? So if your ellipses are, they are very long in one direction and very short in the other, right? So that kind of a cost, if you see the cost behaving in that manner, right, that basically means that problem is not very well conditioned. And if you use kind of vanilla gradient based methods, or even other methods, right, the conditioning impacts the convergence rate of those kind of methods, right? So what we are trying to do essentially is kind of get this condition number, somehow make our problem robust to conditioning of data, right? It doesn't matter what kind of data I'm getting. I will converge at a given rate, and it will not depend on the condition number of the data. So that's one of the significant things that we are trying to achieve, because all methods, although they may be same in the rate of convergence, but the factor which is hanging outside there, right, which it depends on the constant factor, will depend on the condition number, and it can really slow things down a lot. And we also will show later today that basically, that it is robust to noise, right? And we can go to, what are called online setting, in the sense that I can do, variations of SGD on this problem as well, where I just pick up one data point and I can kind of optimize it. I don't have to do kind of batch gradients, on these kind of problems. So these are some of the publications which are there. And so basically what I'm going to talk next is kind of a summary of some of the results and some of the numerical comparisons that essentially you will see. So what exactly we are doing? So let's go start with the linear. As we said, we are working with the linear cost, right? So your linear cost is there, right? So if you, it's a summation of the linear cost over all agents. We have small m number of agents, right? And so if I take the gradient of that, what you'll find is the gradient is kind of given by this expression that you see there. So this quantity, which is AI transpose AI, that kind of really impacts the condition number, right? That matrix that you see there, it'll impact the condition number and will directly impact the convergence rate as well. So what we are trying to do here is that instead of doing what you're seeing on the top, which is the vanilla gradient descent, right? What we are doing is we are multiplying this. We are, basically multiplying this by everything is same, but you see kind of a matrix K that is popping up there on the slide below, right? Which on the expression below, which basically says delta K times a summation of these various gradients across different agents, right? So ideally, if the data was not distributed across agents, and I didn't have a very crazy dimension D, right? Because I can use Newton methods, right? Newton basically, I just have to take the inverse of, I just have to set the K is equal to inverse of A transpose A, and I can kind of, converge pretty fast, right? In this case, it's a quadratic cost. I'll converge one step, right? So we can do it pretty fast in this case. So the problem is that I can't compute A transpose A inverse because it's spread across and my data is not located at one place, it's spread across, right? And the other thing is that kind of this method scales. If I take the inverse, I will have to, it's order D cube, D is the dimension, right? The dominant thing is D cube, right? So we kind of want to avoid taking that inverse here, okay, in what we are trying to do. So what essentially we do is we have come up with an iterative method, right, which basically converges to kind of the Newton method in some way, right? So that's essentially what's happening. So this is the algorithm which you will see kind of across the various variations I will kind of talk about today. So what does the algorithm go like? So you basically compute, I have data set AI at my end. I'm the local server or sensor or whatnot, right? So I basically compute this local gradient for my cost, which is AIX minus B transpose AIX minus B, right? And this gradient is what you see on the top here. And then we compute these Rijs, right? And there are D of them because I have D dimensions, right? So they are D of these vectors that I'm trying to compute. Ej here is just the unit vector. If you imagine that I have a D-dimensional identity matrix, and these are the various columns of that. Okay, and M is a number of agents, right? And beta is something that we kind of assign. So we'll see some of these parameters come up later. And so we compute D of them, right? We transmit to the server. What a server does basically is it computes, this KJs, it updates them. So I was using KJ here. So now I have new KJ update, T+1 updates that are coming about. And they are relying on these updates that I computed from all agents because the summation is from 1 to M. Okay. And I do it for all the D KJs. So I will basically have a new vector now, right? Or new matrix, right? Which is basically there. And now I will transmit it to, again, the agents, right? In the matrix KT and XT+1 is transmitted. First XT is updated in this manner, right? So it's basically a step size, which we'll decide later, right? Times the precondition matrix KT+1, right? And this process continues basically. So, and you can see, yeah. So we'll now talk about like the convergence rates, right? So, these conditions will look a little bit hairy, right? But essentially, let's look at the two unique kind of, cases we have. So if you have a unique solution to your problem, right, it's strongly convex, right? So unique solution to your problem, you basically will converge superlinearly. Okay, so that's the convergence state that you get here. And if you have multiple, then basically you converge linearly, right? Multiple solutions, then you will converge essentially linearly, right? And there's some conditions which can easily be met. And so these are the two kind of convergence states we are getting out of this this method. So now let's make a comparison, across methods, right? So we have a variety of methods that we see there. So which is Nesterov accelerated gradient, heavy wall method, APC, and BFGS, and of course the vanilla gradient descent, right? So if you compare the convergence state for the case when we have unique solutions, so we have superlinear and BFGS also has superlinear rate, right? Everything else has linear convergence rate. If you have multiple solutions, then we have shown that we are linear, but we converge faster than gradient descent. Okay, and so we have a theoretical proof for that we can actually show that. And some of the other methods that we see, either it's not known explicitly what the convergence rate is, right, or in some cases they actually may not converge. Okay, so these are basically the broad comparison of the convergence rates. Any questions till now?
Any questions from anyone?
Sir, just one quick clarification related question. So yeah, it looks great, like the proposed algorithm achieves a superlinear convergence rate. So I was wondering what would be the price to pay to achieve the superlinear rate as compared to other algorithms which don't achieve it, or VFG?
Yeah. So basically compared to BFGS is same. It's order D square, ND square essentially.
I see.
Okay. And so basically, it kind of ultimately depends on what kind of error you want. And a product, it's basically a product of those two things, right?
Okay.
So yeah, so if the D is not too bad, you want to basically outperform kind of existing methods.
Okay, sir. Okay, thank you so much.
Sure. So these are kind of the numerical. So we kind of took some data sets, right, and we tried them on tried this method on these data sets, right? And so you look basically here the condition number. These are kind of second column is talking about the condition numbers, right? So here it looks like, so, and by the way, this is the case with unique solution. Okay, so all of them have unique solution. So what we would have expected is the BFGS and our method, right, both converge superlinearly, right? So we see that BFGS actually is doing pretty well, right, when there is no noise and you basically have unique solution, right? So we now will talk about the case when you have noisy data to kind of see what exactly is the impact of noise on this. So in this case, there are kind of two kind of noise that we can you are handling here. One is observation noise, right? So your data may have some noise in it, or basic process noise, which may come due to some uncertainties in computations or some quantization errors, noisy communication channels, right? Or basically various other things that can be possibly there, right? So we'll kind of handle both of these things. So what we have shown here is that it's robust against observation and process noise. Right? So you can add that, and we have computed explicit bounds on them. Like what is going to be the error bound that's going to come as a result of the noise. So this basically is, let's say again, is observation noise. So your B is kind of you're experiencing noise here, right? So now the assumption here is that that A transpose A is full rank, and also that the expected value of these noise that is there is less than some eta, right? So if you look at the eventual convergence rate, right? So it basically what you'll find is that the final error after the transients kind of go out, right? It depends on delta, which also impacts the convergence rate here. Okay, eventually, because these will die out as as increase iterations, right? These terms 1 minus delta will remain here, right? So if I try to make it smaller, right, and try to make delta bigger, I will impact the final error bound as well here as well, right? So that's what you see there. And it also depends on number of agents that I have, right? So this bound depends on that. And similarly, if you have process noise, right, so you kind of you can get a similar bounds, right? And the details are in the paper. I'm not going through these bounds in detail, but just to get a sense for them, so we can essentially handle both of them. And compute bound on the expected error, right? So now what is the, let's see how the things behave, right? The algorithms that we saw till now, right? So if we have process noise, right? So let's say observation noise, right? So BFGS and IPG, they are, hugging close together, right? As we would expect, both have superlinear convergence, right? But what we don't have with BFGS is robustness against noise, right? So you see that here, right? So you have observation noise, right? Different data sets, noise level for the observation noise is given here, and process noise is the order is the noise level is pretty small. Otherwise it can really, kind of take off different. We would expect that process noise won't be that much as compared to the observation noise. So you see here that in some cases the BFGS basically, even though it's kind of saying that it's going below a certain limit, right? This is the error that you're seeing there. So we can outperform in some cases. Basically, BFGS will just blow up. Okay, so because there is no inherent guarantee there that you are robust to kind of different kind of noise, so you have a chance that you'll blow up. And yeah, so yeah, in this case, right? So now let me just make sure. Yeah. And so we also ran another version of these algorithms. So these algorithms basically, one of the other things that we had done here was that these are, by the way, if you don't know about this, but these are, SGD basically means stochastic gradient descent, AdaGrad and AMS grad and ADAM. They are variations of gradient descent. So these, what you see on the right 4 columns, they are essentially, think of them as like diagonal preconditioners. So what is, just to give you a sense of what is AdaGrad? So in a normal gradient descent, you would have, just your gradient multiplied by the learning rate. So what you do in AdaGrad is that you kind of compute this, gradient transpose the gradient. You compute that running sum, okay, throughout your iterations. And you divide essentially your, gradient descent by that number, which is the running sum of gradient transpose gradient plus some very small thing to kind of make sure that your denominator is not, making system blow up. Okay, you can go if it's a gradient is 0. ADAM kind of is one of the most popular methods which is out there, right? Although people have developed other variations of them as well currently, for example, ADA belief, there are other kind of optimizers which are out there, which are very popular in training deep networks, right? And so when ADAM, what happens is similarly as in AdaGrad, what was the gradient being divided was the running sum of the gradient transpose the gradient of which the scalar. Just think of it that for each dimension I have gradient square. I'm computing the gradient square for each dimension, and I'm basically computing the running sum, and I'm dividing the gradient by that. In ADAM, instead of doing this, what actually happens is they compute the exponential moving average of the gradients and the gradient square, if it's each dimension. Okay, and they basically multiply by the exponential moving average of the gradient divided by exponential moving average of the gradient square. Okay, so these are the methods which are, but in some ways these are like very specific kind of preconditioners. They are diagonal preconditioners. Okay. And so now in this method, we wanted to compare with them, right? So we basically took up the stochastic version of this problem in the sense that I am now no longer computing the gradient on the full data that I have, but I'm picking points from that data set. Even locally, I have some data, so I'm picking some points from that. And this is the kind of the way to go right now for problems. For various reasons, right? Gradient basically takes a huge amount of time to compute for large data problems, right? So we don't actually want to do that. So when we do this for compare a method against these problems, we also adapted our method to kind of in a similar setting, where now each point is being picked randomly by the agents, right? And then the server is also picking up the case it is coming randomly from one agent and updating it. Okay, so we are there's a randomized version of basically our method, right, which is the IPAG, right? It's a randomized version of that. So what you see here is that as the condition number starts increasing, right? So these various data sets are in increasing condition number. What you're seeing here is that we are it jumps from here to here in terms of the order the number of iterations, but it's more or less order 10 to the power 4. The other methods start, still somewhat similar, but then they start taking more and more number of iterations, which are a order worse, right, than what we have. And what we have seen is that and I'll talk about it later as well, that the generalized, what we call the test error, how the methods generalize, right? They're also comparable. It's not that I'm losing generalization by adopting this method. Generalization basically means that, I have some data I've trained on. Now I'm trying to apply it in the other, similar distribution, right? Which data which I have not trained on, how it's going to behave there. So we are not losing any, I'll show another version of that problem, which is more related to deep neural networks later on. Okay. So then basically we kind of come to, learning over general communication graphs, right? So how do we do that? So now in this case, what is happening is now there is no central coordinator. The central coordinator is now out of the window, right? And basically I have, a bunch of machines, right? And all of them are kind of have some data on them and corresponding labels, right? Or they are sensors, right? Which basically are, they have some observation matrices, right? And they have some knowledge of the overall process as well. Okay. So because the reason I'm talking about it, because we'll apply to a distributed estimation problem. Okay. So now you do this and you basically have some system noise as well there, right? So what we have kind of shown is that we have improved linear convergence over distributed gradient method, right? And also improve robustness, in terms of that we are kind of robust to noise as well, right? So in this case, there's no central coordinator, but I have to compute this inverse. So this is a computation, can be a computationally complex, although I do it only once, but I have to still compute the inverse, right? So this basically is, it depends on the local, alpha, which is decided in this constant alpha is kind of comes out of our theoretical results, which I'll show on the next slide. Right, and this Ni here is like, it's basically mentioning it's Ni indicates a set of my neighbors, what are out there, right? And the bar is basically the cardinality. So how many are there, okay, times the identity matrix. So this basically I have to compute initially for each agent, right? And then the update basically happens in this manner, right? So there is no central coordinator, as I mentioned. I compute the GIs, right? And I, delta is again a step size, which is computed in next slide. We'll show what delta is. Alpha is also on the next slide, right? And everything else is kind of similar. I'm getting these updates from the other agents. I'm updating my own, basically based on my own information, my own gradient for the cost, and what the other agents are also indicating. Okay, and this is basically running across all agents. So also we have noise, right? So noise there in X that is there, right? So again, this similar as before, we are assuming that I have some upper bound on the expected value of this noise, and this basically this is kind of a parameter rho, and it depends on a matrix M, which is a very hairy matrix, right? But it's matrix that depends on the on the graph and the individual agents, right? And so these are the kind of the conditions for delta, right, that we have here. And so what you see here is that again we get kind of linear convergence. Okay, rho is rho is less than 1. So the bound for rho is less than 1. So I get linear convergence rate here, but I also have this error that will come because I'm kind of I have noise, so I will see some error there as well. So this is for the connected graph case, right? And we also have kind of results for the case when we have essentially multiple solutions, right? So we can show similar bounds in that case as well. Now in this case, I have another hairy matrix N, right? And basically is kind of the, in some ways, depends on the eigenvalues of this matrix, right? So two matrices kind of are deciding what the row I have to satisfy this, right? And the row is again less than 1, and we can kind of get linear convergence here again. And we can do it for undirected graph, unique case, multiple X, directed graph, and unique. So these are the cases we have theoretical results for. So again, as I talked about that now, think about this way, that I'm trying to solve a distributed estimation problem, right? So I have some central process which is running by its update equation could be xt plus 1 is equal to ax, right? That's my process which is moving. and I have these bunch of different sensors, right? It could be a tracking problem, distributed tracking problem, or just some sensor measurements I'm trying to do for something, right? So now, basically in control systems, we have something called the observability matrix, right? So this OIs that you see here are, so to solve this basically this problem, right? I only need to figure out what the initial estimate or what the initial value of my state was, and because I know my matrix A, I can compute, future evolution, okay, of this. So then this boils down to basically solving a linear equation, okay, which basically is, I have these measurements on the right hand side, I have the observability matrix, and that's multiplying my x0, which is the initial state. Okay, so again, because this big matrix, which is observability matrix, we denote it as O, capital O, and I can break it down into these small OIs, okay, which are kind of spread across different agents. So every agent can compute this OI matrix locally, right? And then we can basically run the similar kind of linear regression problem that we talked about, right? And we can figure out the state in a distributed manner. And we've also shown that we have some robustness to noise, right? So, which is something that, is we haven't seen theoretically that well established in corresponding distributed observer literature that is out there. Okay, so these are some of the earlier works that have happened in this area. And so as you can see here that, we can converge, much faster, right, than most of the algorithms out there, right? And these are the algorithms are listed here, right? And we also achieve much less error in this case. So, although this system is not a filtering, we're not filtering the noise in some way, right? But we can estimate because we are not assuming specific noise statistics and stuff like that, right? So I'm not doing any kind of filtering here, but we can get pretty good bounds, and it's not that we're going to diverge if there's a noise, right? So now let's take all of this. This was for linear kind of systems, right? How can I extend it to general convex cost functions, right? So now it's a more general case, right, which we encounter. And so does our method scale to these kind of problems? So luckily we, a very similar algorithm that we have, right? We can show both, we can basically achieve locally nonlinear, superlinear convergence in, if you have a unique X. Okay, so again, strongly convex, right? So in that you have a unique solution, right? So I can basically get local superlinear convergence and local linear convergence for convex problems in general. So what is the algorithm? This is the algorithm, very similar to what we saw on the first time when I showed you the algorithm for the linear case. So there you had A transpose A, but now in this case you have the, basically the Hessian essentially in some way, right? So I have this, right? And everything else is very similar to what we had on the first slide. Okay, and these again, there are some, beta is not required if it's strongly convex, right? If it's convex, I will require some beta here to make sure that this matrix is kind of, is invertible. Okay. And similarly, we have a very similar update, in updating this Ks and Xs, and I'm, sharing these KTs and XT1s with the agents once I have updated both of them. Okay, so what are the convergence states? So, so you see K star here, right? So this is K star, right? And this is like, so that's why I need, beta to be greater than 0 if it's not strongly convex, right? So if I have multiple solutions, right, we basically have linear convergence rate. Rho here is, is between, is less than 1, right? Sorry, greater than 1 in inverse of that, right? And basically, so we can get this. And this condition, we have to figure out alpha according to these two conditions, minimum of this, which you can choose, right? And we have a simplified version of these conditions in the paper, which I have not mentioned here, but you can simplify them under certain conditions, and it's possible. So again, if it's a strongly convex, we get locally superlinear convergence. Okay, so that's the thing. So how can we apply it? Because now I have nonlinear costs, so maybe I can apply it to general, neural networks and see how we can, how do they perform there. So there is a version in the literature, right? It got, forget the year this paper was published, but they basically showed that a noisy quadratic model, a very simple quadratic cost, but it's noisy, right? And there's a certain way of selecting this cost, selecting that H matrix, the Q matrix in there in this cost, quadratic cost, that if you selected that way, it's as if you can basically test this. This is a very simple way of testing how your algorithm is going to perform on deep neural networks, right? You don't have to run that. You can basically use a simple noisy quadratic model. And this got published in NIPS in one of the years. I forget the exact year where this got published, but it was in recent past. Okay. And people have been using this model to essentially see how they are going to do well. Okay. So for example, for this problem, our D was 10 to power 4. And the condition number was also 10 to power 4 in this case for this problem. So here you can see that BFGS is, it will diverge, very fast, right? ADAM does well, right? ADAM converges fast, right? But, we are able to kind of converge, in sense our algorithm is able to kind of get a better rate, right, after some time, right? So that's what kind of the superlinear convergence kicks in, and we kind of see that. Yeah, and other methods are also there. So gradient descent is just sublinear. In this case, it will be linear, but in general, gradient descent is sublinear convergence rate. So basically, you can see that vanilla gradient descent is not going to take you nowhere. Okay, as we know from a variety of methods. So let's look at the we did some. So this was with the noisy quadratic model. We also took a logistic regression problem, and both with MNIST and Seifert data sets, and so we see that we can compared, so this converges much faster than anything else that you're seeing on the slide, right? The only comparison is BFGS, but here also you see that although this goes below a tolerance limit 6 in 10 to the power minus 8 in 43 iterations, it blows up soon after that. Okay, so anytime a noise kicks in, BFGS gets really uncertain. It can go it can, you can get lucky, and you will get very fast convergence, and actually that's where you want to converge, or it'll just blow up and after some time, which we are seeing here as well. Yeah. And these are again, these are what you're seeing here is the cost, right? So after some time, so you can see that BFGS kind of blows up, right? So and we are at similar cost in less number of iterations. And by the way, so in this case, this is reflecting actually in some case a training error, right? But we also have so what we saw was that when we took a test set and we kind of tried a model there, or the learned model there, so we were getting similar generalization errors. Okay, so we are converging faster, but we are not sacrificing the generalization capability compared to these other methods that are out there, specifically ADAM in this case, right? So the remaining time I have, right, I would like to focus on what we have been doing in the ArtIAMAS project, right, an application to basically distributed beamforming, right? So how we can do that. So in this problem, what we have is that we have a bunch of beamformers, and we are trying to basically, we have multiple beamformers, and basically we are trying to select their amplitude and phase correctly, right? So that essentially we are getting constructive interference at certain radial directions and certain distance, but in certain locations, we are getting constructive interference, which basically means that my directional signal has very good power in that direction. On the other hand, I'm getting destructive interference at my desired locations as well. So simultaneously, we have to achieve, constructive interference and destructive interference at various points, in the coordinate. Right now, it's a two-dimensional problem, so we are focusing on 2D plane, right? But we have to achieve that. So, so in this literature, we have something what is called the array factor. Okay, so the array factor depends on my location. So these are transmitter locations. Rho I and theta I are the receive locations. Okay, and and di is basically the distance between the transmit and receive locations, right? And essentially, we are trying to kind of optimize essentially for these alphas, right? Alphas and the amplitudes, right? And so essentially, at each location, right? Basically, I am formulating, I have various transmitters coming in, right? So these are the S is the number of samples where I want, essentially, I want this power at this location, this power at this location, right? So each FI essentially is kind of a sum of what I'm seeing at different different transmitters coming together. They are computing this sum, okay? And I'm minimizing, I have some desired power that I want there, right? And I'm trying to minimize this cost across all samples. Samples meaning that, locations where I want certain power. So we can have this same problem, right? Formally use the distributed method we have for each agent, right? And solve it. So in this case, this is kind of the spatial location of the agents. Forget the exact number of agents, maybe around 19, maybe. Okay, and so we have 49 locations where we essentially want a desired signal, whether it's so if you look at the plot on the right, you look at the dotted plot, a dash plot. So what you see here is that so this is relative power in dB, right? So basically where I'm seeing the lowest dB, I want nulls essentially there, right? And I have highest power at particular location and other places in between them, right? So the dashed line is kind of showing the desired profile, right, across 49 locations. And this is the theta that we have, right, which is reflecting that. So now what we see here is that if I implement vanilla gradient descent to solve this problem, right, you can go to as many iterations you want, right? You will essentially head nowhere to solve this problem, right? On the other hand, without any explicit feedback, so I'm not this is like an open loop problem. I'm not getting any feedback from the receivers right now. Okay, so there's no feedback from the receivers. I don't even know the channel gain. Okay, the fading parameter, I don't have any idea of that fading parameter. We are not estimating that. So this is actually what is happening. But in my optimization, when we are assuming that I don't know the fading parameter. Okay, so without knowing those some of the channel parameters, we are able to kind of achieve pretty soon within some desired dBs of your desired power at various locations. So what you see here is that sometimes we are matching the nulls better than the where I want high directional communication. So sometimes it happens that there is a mismatch between the two, that one matches well, the other doesn't. To kind of counter that, we put weights here, right, to kind of weigh each of these samples that you're seeing in a way. And so although we haven't done it right now, we are trying to optimize. It's like a nested optimization problem where we are trying to optimize these weights as well, these WI as you see here, and also the basic optimization problem. So essentially, it's like an iterative optimization problem. First, I solve one, then I fix it, solve the other, and go back and forth till I converge to, I'm not getting any better solution than before. Right, both of them you can add. So if you look at this, yeah, this is linear in these weights. It's non-linear in the other weights that we have here, right? So we can either apply IPG on both of them, or if you wanted to just use the vanilla, if it's linear in the weights, I can always use the pseudo inverse and solve this problem as well. So we haven't done it yet, the iterative optimization, but that's something that we are going to do next. And we also have done this for some real data. I'm not showing it today right now, but we have simulation data with a realistic environment in LA, right, and which has buildings and forts. So there is a lot of real propagation happening there. And so our preliminary results, which we have developed, they indicate that we can perform quite well there as well with this method. Yeah. So we are kind of looking to use this method and see what to do with it as we go forward, right? And yeah, so just want to kind of close the talk. So maybe have some questions if people have questions, right? So basically, the idea was that we have a new formulation for distributed and decentralized optimization, and for both learning and general distributed estimation problems, we have some preliminary kind of results which indicate that we have favorable behavior in terms of both. In terms of convergence, definitely, and we are not sacrificing generalization. And specifically, we can achieve superlinear convergence, right, with the added benefit that we have noise robustness, which is not present in the current method, for example, like BFGS, which have the same order as us in terms of computational cost. And as I showed that this is broad application in several domains, right? So for example, I showed you an application in distributed beamforming and also distributed estimation, and of course, learning, broadly learning as well, right? And so for this project, an ArtIAMAS project we are using this optimization framework as a foundation for various mission and autonomy objectives. So we have just kind of have some preliminary results right now on one of these things. So going forward, we hope to kind of generalize this framework, and we have a lot of mobility problems that we haven't tackled yet that we'll kind of see how we can utilize this framework there as well. Yeah. So I'll be happy to answer any questions if there are any questions at this time.
Okay. Thank you, Dr. Chopra, for the excellent talk. Any questions from the audience?
One question I had is, what are the physical constraints on the conditions where this solution works well, perhaps like number of units or distance between them and things like that?
Oh, you mean a specific beamforming problem?
Yeah.
Okay.
Yeah, for the beamforming.
So basically there is a wave number constraint that we haven't put in there. So that was, I was talking about the mobility constraint. So if they are too close together, right now we haven't modeled the mutual coupling between the agents. Right. So so what we actually hope to do is, so now if you think of this problem from a robotics perspective, what we typically do is we have what are called, we have these think of them as bubbles around us, right? So when its agents are moving, I will not let any agent come within X distance of me that is somehow related to the wave number of my transmission. Right. So we will explicitly impose those constraints in mobility, which we haven't done right now. That's what I was saying, that some mobility aspects are remaining, but then that will kind of at least handle one of those things, which is the mutual coupling. Yeah. Thanks. Any other question, folks?
Any other questions? So, Dr. Chopra, I have a quick question. Like you said, like in a multi-agent communication, some of the agent needs to communicate the parameters to the centralized server or to the other agents.
Right.
So how do you solve the local minima and global optimization problem there? Like, do you need the entire picture to the local agent to communicate the appropriate parameter? Can you talk a little?
So basically there are only few things that, for example, beta. So
Okay.
beta is is beta and alpha are something that you need to communicate to all, Well, actually, if you have centralized case, if you have the linear case, then alpha is being computed as server, so I don't need to send that, right? But
Okay.
agents need to know what M is, what are the total number of agents out there.
Mm-hmm.
So maybe you can run, let's say you can run a simple algorithm to compute. Even that can be computed in a distributed manner. How many agents are there in the network?
Okay.
Right? I want to figure out how many agents are there in the network. There is no central, either the coordinator can tell me, everybody, these are M agents in the network, right? Mm-hmm. Because I need that M in my local update.
Okay.
So a couple of parameters I need in local update which the coordinator can share.
Okay.
But there's just a couple of them,
Okay. Okay. Okay, that's great. Yeah.
Yeah.
Any other questions from anyone? Okay, one last question maybe from my side. Have you done the computational complexity analysis of some of the approaches?
So it's order MD square.
Okay.
So D square is what is the dimension, is what is it's second basically, so yeah, so basically, it's the good thing about the gradient based methods, right? And even SGD, right? So it's order D, right? Actually it's ND, but what happens is that eventually it boils down to what kind of error I want, right? So it's a function of basically, ND divided by epsilon in some way, where epsilon is the error, right? So these methods, the problem with general gradient descent is that, it's order 1 by epsilon, right? Depending on what the error is, right? So it doesn't converge very fast, right? Until I have a very nicely behaved function. Yeah.
Okay.
Yeah.
Thank you. And any other questions from anyone? If not, let us thank Dr. Chopra again for his excellent talk. Thank you so much for.
Thank you.
Thank you. Let me stop. And